Hi everyone, my name is Chen Cao. I'm a student of electrical engineering major in Texas State University. This is a record of presenting my individual project for the course Forecasting and Simulation. My professor is Dr. Lawrence Fontaine, who is a very talented data scientist and a very helpful teacher. For the final project, we need to shoot a video about a project we finished. In the video, we explain what we learned and implement in the forecasting and simulation class. Well, let's start. I got the real data from online, searched the time series, seasonal data. Then I obtained it from a data website called datamarket.com. It's a CSV document containing 10 years everyday Melbourne's lowest temperature recorded from the January 1981 to the December 1990. After I read into R, my raw data consists of the time with no obvious trend. The point is daily recorded, so the frequency is set to 365. The data has a size of 3,650 observations. For a better understanding of this data, I plotted the main feature I'm interested in. The first one is a histogram plot of the data. It shows that the data distributed normally well. The second one is a linear regression data plot. It also shows the plot meets the normality assumption. The third one is a seasonal plot of every year. I use the rainbow color to show the difference of every year. Let's see the seasonal plot to look a little bit about the data detail. The temperature in the beginning and the end of each year is higher than in the middle of the year, so quite different from the north part of the Earth. The fourth one is a seasonal decomposition plot. I used the STL function to decompose the time series. The plot shows the function divides the data to three parts: the trend component, the seasonal component, and random point. It has a regular pattern of up and down fluently, and it shows the obvious seasonality of the data. If there are temperature increase, like greenhouse effect, we need to use a model with a trend, but now here we don't need to. I also plotted the moving average with a parameter of k. It makes the data with less random data, especially when k equals to 35. When you use the MA function, we'll see the bigger k is, the smoother the image line shows. There is no typical theory for optimize the k value, so we just try different k for the data to find the best one. Then I applied a ETS function to fit a model. With the ANN parameters, I use forecasted function to predict the future value. To see more efficiently, I plot the result. In the ETS function, the TS is the time sequence to be analyzed. There are three letters to limit the model. The first letter represents the error term, second letter is the trend term, and the third letter is a seasonal term. The optional letters include A, the addition model, the M, the multiplication model, N, which is a noun, and Z represents the auto-select. In this case, I can only choose the ANN model or the auto-selection model ZZZ. Both models give me the same result, but the result is not good. It shows a straight line as a predicting value, so it's time to improve it. We can see the ETS function automatically selects the best fit of the original data model. But here, because the frequency number is larger than 24, the ETS function can't handle it. Use the ETS model, it'll ignore the seasonality so I tried another named STLF function. Now we get the seasonality back. From the plot, we can see the forecasting here works better. It follows the seasonally and predicting the up and down quite well. The confidence interval also follows the up and down. It becomes wider later since it's more difficult to predict it in the future time. I didn't include the hot winter model here because it doesn't fit the data. Let's talk about the ARIMA model. ARIMA model is a tool for understanding and predicting future value in this theory. It consists of 3 parts: autoregressive AR part, and the moving average MA part, and I is the integration. The AR part involves regressing the variable on its own lagging values. So, observe the time series data, we can see the stationarity is good. It doesn't need to be transformed. The variance is very close to 0. Use the ADF test function from the TS series package. Get the p-value. It is very small. The result is significant. Also use the differs function from the forecast package. It calculates the difference is 0. So R tells us it doesn't need to be differenced. And then I plot the ACF plot, which is a autocorrelation function, and a PACF. It is a partial autocorrelation function. It is to check the parameter D is right or not. The ACF seems from 0, the accuracy is decreasing, so it evaluates the above D value can be used. You can identify the number of AR and MA terms that are needed. ACF plot is merely a bar chart of the coefficient of correlation between a time series and the lags of itself. The PACF plot is a plot of the partial correlation coefficient between the series and the lags itself. The PDQ, this is 3 important parameters of ARIMA model. P is the number of autoregressive terms. D is a non-seasonal difference needed for the stationarity, and Q is the number of lagged forecast error in the prediction equation. It can be generated automatically from the auto-ARIMA function and verified in ACF and PACF plot. I used the auto-ARIMA function to generate a best PDQ parameter order. The order is used in following ARIMA function as one group of the parameter. I had my first ARIMA forecasting. It looks everything is done. I tried to forecast the short time and the long time to see. Unfortunately, I found it works for the short time prediction. For the long run, it seems too flat to be a forecast. I also solved the minimal solution of AIC. The result will be an ARIMA and a PDF parameter form with the optimal solution. In my case, I use a loop of finding the smallest AIC value, so it can go through a lot of parameters very quickly. So I have to think about what caused the flat problem. Also, I'm pretty sure it's not a forecasting that I want. I know it's not being perfectly predicted. After I think about that, I found the error is caused by too long period frequency. How to overcome the problem? I searched how to deal with the long frequency since I changed the frequency. The result changed the PDQ order number. I think about how to eliminate this error. It seems that the problem is because of the frequency. It's too large than the usual. So I searched the solution. I found the Rob Hindman. He has written how to deal with the long frequency in his blog. According to Rob Hindman, generally speaking, the seasonal version of ARIMA and the ETS model are designed for shorter periods such as 12 for monthly data or 4 for the quarterly data. For such data, he preferred a Fourier series approach, where the seasonal pattern is modeled using Fourier term with short-term time series dynamic. Allowed in the arrow, I use Fourier method in ARIMA function. With the information, I got the forecast plot like this. There are some potential best model here, so I tried them one by one. It almost gave me the similar result, but slightly different. After that, I checked the accuracy to see the MRSE. MRSE is a square root of mean square error. It presents the variance size of the model predictive value and the original value. It doesn't come with a unit, so we can use it to compare the prediction accuracy between different time series. Compared to before, the ETS and STLF model, the ARIMA model with the Fourier, which is above, has less MRSE than the STLF, ETS, and ARIMA model before. The 2.48 to 2.35, you can see it's very obvious, so it proved to be better than all the other model to fit and predict the data. This is my data set and the reference here. Let me summarize the work I've done. I basically used the ARIMA model with the Fourier term to forecast the minimum temperature because it works the best. From the work above, I think a little bit about the forecasting. Firstly, we can't decide which method perfectly fits the data until we start to deal with it. Most of them can be fit as model, but some of them it's hard. It depends on the experience a lot. For this case, if I didn't find the Dr. Roberts blog, I'm sure I can solve the problem maybe with a long time, or maybe I cannot solve the problem. For the parameters, there are lots of parameters possibilities in the forecasting. So sometimes we can determine a range of them, sometimes we need to try. So there's still a long way to study forecasting using R. Thank you very much for watching, and thank you all my classmates, and thank you for Dr. Lawrence, whose class is very well organized and time efficiency. He's always the most nice and helpful teacher I've ever met. Thank you guys for watching my video. If you are interested in any question about it, please email me at c_c6one@txstate.edu. I'll share my data, code, and my opinion with you. I wish everyone has a nice experience with learning R. Have a good day.